Welcome to this class on measure theory. Today, October 29, 2020. I chose to pre-record this class because of the complaint that I have got from students that sometimes they are unable to access the class continuously live. So I thought the video will do them justice because they can check on the notes at their free time, so that if you don't have bundles where you live is where you can come and continue. I had tried to use the big blue button equally, but I realized the big blue button that the video comes after 2 hours, and after they've come, they disappear within 7 days. And so that was not being conducive to students because some may not have joined their class within 7 days, or they are not able to download. So, but this one, I have decided to give you the link so that you can go to YouTube and access them at any time that you deem necessary for you when you are free. Uh, Today we will just continue from what I have given before. So I will give the notes on, we'll start with the set functions and measures. I will try to explain what is a measure interconnected with the set functions. We will try to see what we are talking about in this context. So what are set functions? Let's define what are set functions. So the set of all real numbers, we're talking about the set of all real numbers, will be denoted as R, okay? The R here should be understood to mean this R, which is the set of real numbers. This should be understood in that context. So not just at the normal R, you just R with the two lines to mean the set of real numbers. But in this book, when you see this capital, this R, which is the uppercase, should be understood to mean this one. These are just the same, the set R. So the set of extended real numbers is the result of adjoining to R the symbols this and this. That means extreme values of the number line, when you adjoin them from negative infinite to positive infinite here, right, to the positive infinite, should be understood to mean this. When you adjoin, you get this R. This is R of real numbers, which is an extended, the set of real numbers, which is the extended real number. So E here does indicate extended. It is now the union of these extreme values from positive infinite to negative infinite. You can define to be just from extreme values. So sometimes it is either from the negative to positive. We are used to say from left to right, but here they are saying from right to left, which means the same thing in that context. So the usual ordering of the extended number is given in this format, and that's what we are saying. The value here in between negative infinite to positive infinite, it is in between for the any real number C. Now, every non-empty set of extended real numbers will then have at least a least upper bound. A least upper bound, LUB, a least upper bound. We have the least upper bound. Then we have the greatest lower bound, GLB. Okay, these symbols here. Least upper bound, and then the greatest lower bound. All right, this is what we call what? The supremum and the infimum, of these of the variables. But that the terms, the supremum and the infimum, are in the context of the real number system. In this case of the measure theory, we are not into that context. So this the R, we call it a complete lattice. Is meant to be a complete lattice. And this lattice here is a context that you can define in it different axioms. You can define it in different axioms. You can talk of the associativity, closure, commutativity. In those contexts, you are able to define them and they put them in that context. All of them can be the existence of the inverse, existence of the an identity, all those can be explained within that context. Now, the abbreviations of least upper bound and the greatest upper bound, lower bound will be used. So if AN is an increasing sequence, we are talking about a sequence which is AN, okay? This is an increasing sequence. That means a sequence whose variables are increasing, they're increasing from the lower to a greater value, the sequence whose variables are increasing, okay? Of extended real numbers. That is, if the value on the left is less than the value on the right. That means on the right, the value is bigger, right? For all n, it can be equal in the case that what? In the case that the sequence is constant, like is the same value, like 2, 2, 2, 2, 2. In that case, then they'll be equal. But usually, when it's an increasing sequence, we expect the value, the next value is greater than the value which is preceding for all n. Then we write this case. This is an increasing sequence. That means the sequence here of alpha here is increasing. In other words, this will be defined to be the least upper bound of the alpha n, this alpha with respect to n, which is the values of the sequences here. So we write this, the value alpha n is increasing to A. The value alpha n is increasing to A. That's what we mean. That means it is increasing to a certain value, which means we are saying increasing to A. The converse of that, or the duo of that, is that this means the value is decreasing. The value is decreasing. In other words, we can say that the value now on the left is greater than the value on the right. Therefore, it means it's decreasing. Like you can move from 3 to 1, you know, you are decreasing in terms of the values for all n. And then we say this, we write this one to show that this is decreasing. The arrow facing downwards means decreasing. Upward means increasing. That means, moreover, that this will define to be the greatest lower bound. Greatest lower bound. Because when you go to the lower bounds, you have the greatest of them. There are many bounds lower, but the greatest of them is this one. This is the value we are, this one. But on this one, least upper bound, there are many upper bounds. There are many of them. There are many of those. But now the least of them is this one. Is this one. So we can talk of supremum and the infimum. This is the supremum, this is the infimum. So the multiplication in R, in the set of R, this one I did say it is the set of real numbers. The set in R is extended to RE as follows. So we define that 0 dot infinite is this is commutative. The commute is the same as when we do it on the left or right. This becomes 0. So while all other products, alpha and beta, are defined in the extended way, like for example, you can just extend that 2, it's only this 0 that changes, but any other value, 2 times infinite is just a negative infinite. So the symbol here, I mean, does negate the positive infinite. The negative negate that, but 2 is a very small number compared to infinite, it will just make it infinite. In fact, it's like this one is changing direction. The negativity here or positivity changes direction. It's like a vector when you come to the vector analysis. The symbols plus this one of the two extreme values, infinite, positive plus negative, and negative plus positive, these are not understood because when you add two big numbers, we are bound not to say what exactly is the result. So they are not defined in this context. Well, all other values of alpha are extended in numbers. These are defined in the simple way that any value, when it comes to the simple small values, this plus the positive infinity, it's simply absorbed. A very small number plus a very large number is a very large number. So the very large number still remains, all right? A very large number still remains. In other words, we are saying, for example, 8 plus negative infinite, this does not change much, it's still negative infinite. It won't change much, All right, that's what we're saying. You can think of many other values which are fixed. These values are fixed, but when they are infinite extreme values, we are not able to define them. These are not defined. They are not defined. Then we can talk of set function. We can talk of set function, and we are saying that a set function here, uh, right? A set function is a function V whose domain of the definition is an empty class epsilon of sets. Okay, this is epsilon of sets. For our purposes, the value of V, this V, will always be extended real numbers. That is to say that V is mapped into the values of extended real numbers here. V maps the value here, the set function, into the extended real values. So a set a function is said to be finite if its values are real numbers. So we say it is finite if the values where they are real numbers. That's when we say that a set function is finite. Now, let V be set function on E. Now, if V, this value is positive, okay, greater than 0 means it is positive. For all E in E, we are getting this E in E. That means this E is contained in this E. This E is contained here. V is said to be positive. We see that V, therefore, is positive. In a brief case, we will put that when the V is positive, because this means positivity, then the set V is seen to be additive in the case that you can get the union. Right? In the case that the union, someone who is, I think, sending me a text or something, I don't know. I was hearing some noise. Oh yeah, someone is texting on the class. That's why I just got some noise, which were not precedented in this. I did not expect to have such noise. No, right? Okay, let's continue. So the union here is defined as aspect of addition. So the union of U and E and F, it's defined that the section wise, the V of E and then V of F. But now you change the union to be the plus. Then we say they are additive. Whenever E and F are disjoint sets in E, when do we say two sets are disjoint? Two sets are disjoint. For example, set A and B are disjoint if their intersection is empty. Then we say those two sets are indeed disjoint. So E and F are disjoint sets in E, whose union is also in E. So if this happens, okay, this becomes disjoint if the V is less than or equal to the F. Whenever E and F are sets in E, such that this case happens, and V is therefore said to be monotone. We talk of monotone when it comes to the real analysis because we talk of monotone increasing or monotone decreasing. In this case, it is just monotone. A sequence that is increasing or decreasing, we simply put it basically to say it is monotone. It is a monotone sequence. If phi belongs to E, that means the empty set, it's part of that, this set here. V is monotone. And then the composition of V and empty is 0. And in an evident, then V is positive. And the definition of positivity has been given thereof. Right? V is positive. On the other hand, an additive positive set function V defined on a ring, this is necessarily monotone. Since E is contained in F, remember our E was contained in F, right? In the case that we did define it, where did we put that? Did we put it? I think we did define it. Okay, in the case that V, E is in F, This implies that F can be given as a composition of F minus E union E, because that which this is a set symmetric difference. Otherwise, some books will write this to be F minus E, whatever you get here, then you union with this E again. You get union with the E again to get this value here. So you are subtracting whatever was in E, then again you add that which was out. All right, so you add that which was not contained. This is what this one minus here means this one. And hence we can talk of this one. This is a result that when you put V of F here, you get this, which is this one. You put again V of this one plus V of E, which is this one. The union is defined as a plus. That's what we said in this case. The union is defined as a plus, okay? So this must be less than or greater than this one, which means it is monotone. It is like the values are decreasing, you know, they are decreasing. Then we can talk of a measure now. And we said, this was set and measure. So a measure is a set function, mu. The mu is our new measure, whose domain of definition is a ring R. This R is just to differentiate from the R for the real number. So this is just a ring on the ring R, such that this value, mu, is additive. It is meet the condition of additivity as we have defined above there. It is positive as we have defined on the case of positivity here. We define the additivity, positive and additive. It is additive, it is positive, the mu of empty set is 0, and the En is increasing sequence in the ring R, whose union E is also in R. Then we can talk of this U to be the least upper bound of En. It's the least upper bound of En, mu of En. So suppose that we get mu to be a measure defined on the ring R. Since mu is additive and positive, mu is monotone, meaning both increasing and decreasing, because we're talking of least upper bound and the least lower bound. I mean the greatest lower bound. So we can talk of this to be monotone in a general setup. And it follows quickly that En is increasing sequence of R of the ring. Then we have this mu to be the increasing sequence, mu to be increasing sequence. Thus, the condition 4, which is this one, this condition here, may be expressed as follows, that En increases to E. En is increasing to E. So like, because we're talking about the least lower bound here, whenever or where En and E belongs to R, to the ring. And therefore, even its measure, even the measure of that, because this was a measure, that this function mu is a measure, then again increases to the measure. So when we put this one, mu of En will increase to mu of E. That's what we mean by this case here. And therefore we express this condition by saying that mu is continuous. We express this by saying that mu is continuous from below, is continuous from below. It's not continuous from above, it is from below. And we emphasize that this En is assumed to be a sequence. This is a sequence just in a usual setup of real numbers. Some of the most important first properties of measure are listed below. These are just some of the properties. I'll give a couple of properties when it comes to the real numbers of the measures, sorry. One, we are giving them in terms of the theorem that this measure, let mu be a measure on R, on the ring R, then mu is monotone. That means it is increasing. That's what it means there. Mu is conditionally subtractive. That's what it means. You can talk of this subtraction, but with conditions. That is provided, you know, this condition here, provided E and F are sets. That's the reason of the condition, because it's conditionally subtractive. In other words, this is subtractive, but with conditions that has to be set. such that this case happens. And then we can we go to number 7. That's the extra theorem. We go to number 7. We can talk of mu is finitely additive. Mu is finitely additive. That is to say, these values are finite. Finitely additive means the values are indeed finite. These are mutually disjoint. These are mutually disjoint set in R. So when you get the union of all of them, this will be equal to this value. It is finitely additive. Finite, not infinite. A mu is countably additive. All right. Again, that means this case, that for all the values that you get union from defined from 1 to infinite, we instead of the union, we talk of addition. You see, the unions are extended to be just pluses, because that's how we did previously here. We did mention it to be where was that now? We defined it to be addition. I'm missing the point here, which I think we did explain, but we did show that it is indeed this here. This is defined to be the addition. So when you see the union there, they are defined in forms of the summation. Union R becomes summation here. This is the countably additive. And this, we are saying what now? We are saying in the sense that least upper bound of the increasing sequence of partial sums is equal to this one. So they're equal. The union, they're equal. That's the explanation there. We don't have to show the proof for that. It's not my joy to venture into these proofs, because it will call for so many narration here, but we can do it later. For now, I wanted you to see those results. So those are the properties of the measure mu, Okay, let's proceed. Theorem 2, this was theorem 1 that we were trying to explain here. The theorem was trying to explain these parameters. Now we are in theorem 2. Okay, so the numbering should not disturb you, because the numbering is the continuation from what was given here. You see, this was 1, 2, 3, 4. So now from there, we are going to 5, 6. So you can just call them 1, 2. That's why we have theorem 1 here. So now we are going to theorem 2. So it's just a continuation. Otherwise, there's no harm into those parameters the way they have been listed here. You just need to understand the book that you're using and how things has been arranged. If R is a ring and mu is an extended real value set function on R, right? So my mu now in this case, the measure is an extended real value set function on R, which is positive, countably additive, and satisfy the condition that mu is 0. That means it is a measure. Then mu is a measure. All right, then it's a measure. Because measure, you have to go through those variables here. We are saying it is countably additive, it is positive, and satisfy this condition, which was condition number 2 there. Then that becomes, it's a measure. That becomes a measure. In condition 3, it was condition 3, not 2. This one. So we must verify additivity and countably and the continuity from below to show that it is the least upper bound. That's the proof for that. You may want to follow if you wish, but it is not my pleasure again to go into the proof. I just want you to see how the theorem comes, how the theorem is stated as a matter of explaining what the theorem is all about. What the theorem is all about. Now, many of the fundamental theorems in the sequel require in the follow-up. Sequel means what is following later in our subsequent chapters or subsequent sections. This require further assumptions of the measure equation. So there will be so much assumptions that you have to make. That when you say a function is a measure, we may not have to necessarily prove it is a measure. So it has been proven in many quarters that indeed it is a measure. So it's not our job, and it's not a joy. It's not that nice though, trying to explain that. For those who might deem necessary to continue with academia, you may want to do masters, you may want to do some, advanced math courses in other quarters to extend on these ideas. You can take these as your area of research, and you can make it more joy. That's where now you go into nitty-gritties. In our case here, we are not into much of those details. So we are saying those assumptions will have to appear. So, but when that comes, then those will be mentioned. So we will have to, we will have occasion to use just two such conditions, finiteness and the sigma finiteness. When it is a sigma finite and sigma and just finite, we will just use those, but those will come in handy in our next section. Now, a measure mu on a ring R is said to be finite, okay? This finiteness is, we say it is finite in case that this mu E is less than that. So when we say a value is less than this one, means it is finite because it cannot be defined on the entire spectrum of the real line. So we have to just pick a few values. So it is like less than, but less than here in this context of mathematics, it means it is finite for every E in E. A measure, this is said to be sigma finite in case, given that this is in R, there exists a sequence this in such that this happens. Okay, U is contained in this sequence and mu is finite, then for all n, all right? This is what we mean by that statement. Then you say it is sigma finite. Because we're introducing the sigma in this case, so then we call it, I mean, we're introducing a measure, then in the case we call it sigma finite. And this sigma finiteness is a simply equivalent thing that every set has to be expressible as a countable union of sets. So this is what it means. You have to express it as a countable union. These sets is expressed as unions, you know, is expressed as unions of all of them. That's what we mean by this statement here. And this values, they are just being explained. And I'm avoiding this, the context of trying to explain what is all this is about. All these are the definitions. But there's an exercise here. Here's an exercise. There's something that is being mentioned here. Let R be any ring of subsets of a set X. If E is contained in the ring itself, define this mu of E is defined to be the number of points of E when E is finite. How many points of E when it is even? All right, and then the positive infinite when E is infinite. So this we define to be the number of points of E when E is finite, and then it is defined to be the case. So you define this one, mu, to be two things. Mu of E, okay, look at the gymnastics now, is defined in twofold. One, this is defined as the number of points of E when E is finite. So this is E, but on condition that this E is finite, the number of points when is finite. Then the second case, this is defined as positive infinite, on the condition that when this is what? Is when E is infinite. So this is limited. The points here, the P, let's call it P, these are limited, or it is just infinite, or is a value that you can attach just to be a value. But this one is when it is infinite. Okay, so we call it positive, but when it is infinite. Then mu is a measure on R, and this measure is given a term. It's called discrete measure on R. It's called discrete measure on R. So this now exercise becomes an assignment. Don't ask what the assignment is about. I don't want you to prove this theorem or this statement here. I just want you to check and read on discrete measure. Read on a discrete measure. Read on a discrete measure. Because when you read and understand about discrete measure, you will have understood the context of what? Of how the question is framed. The framing of that question, which is this one, will come in handy here. Now the assignment goes. When you read, I mean, when you've read Summarize your work in a page. Summarize your work in a page. When I mean a page is just a page. This sheet of paper, one side only, on one side only, on one side only. Take a photo or scan it and then send it to me. Then send it to me. That is the assignment that governs this problem. When that happens now, I'm certain you will be in a position to understand how the question is framed. How the question is framed. Next, we will look at the properties of a measure. I will send again lecture on these properties of a measure. All right. So things to ponder. One, do this assignment. Two, the things that will run quickly. I want you to check on what? The properties of a measure. Properties of measure. So that you can understand what are the properties of measure. Is a monotone, subtractive, additivity, all these ones. You really have to check. Countably additive, you have to check those properties. These are some of the properties. Others will come in my next class. So that if I say, which of the following is not a property of a measure, you are able to pick and say, this is not a property of a measure. Let's end there for today. Have a nice time. For any question, contact me. Enjoy your time there, and may God bless you. Thank you very much.